Good afternoon, I'm Doug Schmidt from the Institute for Software Integrated Systems, or as we call it, the Institute formerly known as ISIS. We've got to work on that one. We're the good ones. So I realize I'm the only person standing between you and the open bar that Bill has promised to buy us as soon as we're done, so I'll keep it short. So I'm going to talk today about some of the challenges of certifying dynamic, adaptive computing environments. And I'm going to use as a motivating example throughout my talk one of the Navy's latest warships, the DDG-1000 Zumwalt class land attack destroyers, as my example to refer to in this context. I picked this particular example for a couple of reasons. I've been working with DDG-1000 for the past 2 decades as a program manager at DARPA, as a professor at Vanderbilt University, as the CTO at the SEI a number of years ago, and there's a lot of software I've helped develop that's running on the ship, so I have a lot of familiarity with what it's trying to do and how it relates to the topics at hand. Another reason I picked this example is because it's a great example of a safety-critical, mission-critical system where the right answer delivered too late becomes the wrong answer. So there's a bunch of quality of service issues having to do with how you schedule and allocate resources, and we'll talk about those things. Another reason I picked this example is because the commanding officer on the DDG-1000 ship is named Captain James Kirk. And that's just like so cool. And I've actually figured out a way to work that into my talk later, as you'll see. So there's a bunch of interesting things about DDG-1000. It's got some interesting hull design, as you can see, very stealthy. It's got some interesting propulsion systems. But what I really want to talk about here, because it's most relevant to the discussion, is something called their Total Ship Computing Environment, or the TSCE. And this is basically a fairly revolutionary approach in modern warship design from a systems engineering and software engineering point of view. Basically, they have 500 plus multi-core computers spread throughout the ship that run all the various applications that they need in order to keep the thing functioning. So for example, it handles the propulsion system and the lights and the radar, the weapon systems, the crew entertainment, and so on. And it's essential to being able to fulfill one of the key missions of DDG-1000, which was to try to reduce the manning or to reduce the staffing and automate many, many parts of the shipboard encounters and operations. What's that? I believe the goal is in the low hundreds. You know, in fact, I'll tell a quick story. Originally, when they first proposed this, it was called Arsenal Ship. And the idea was that there'd be two parties on the ship, a dog and a man. And the dog was supposed to bite the man anytime the man did anything other than let the ship run itself. So that was the original story. So they have a few more people than that. One of the things that's interesting about having a total ship computing environment is that you can start to do dynamic resource management and dynamic optimization of the systems on the ship. So here's an example. These kinds of ships carry out many missions at the same time. They have offensive and defensive information warfare, air defense, ballistic missile defense, land attack capabilities, and so on. And at various points in time, you may need to readjust these things. If you're in the middle of an information warfare experience and all of a sudden your radars detect an incoming cruise missile, you probably want to switch to the air defense mode. Or as the real Captain Kirk would say, all power to the forward shields, right? That's what he would say. So that's dynamic resource management as we come to know it as Star Trek fans. DDG-1000 was a big advance over previous approaches to the same type of problem. So previous approaches tended to use a number of very hard-coded things. They used proprietary computers, which were ironically called yucks. They had point-to-point interconnects, which were very fragile and very expensive to develop. Limited growth capacity. A lot of these ships were built back in the late 70s and 80s when computing wasn't as important, so there was really literally no room for it. Tightly constrained stovepipe solutions, which are vendor-locked and hard to evolve and hard to change. Highly vulnerable to damage. If any parts of the computing system get damaged for whatever reason, the ship is basically a floating dock at that point. But the most important reason for the context of this discussion is these systems were statically configured. The resources in the ship were statically configured. And what that meant was when the ship steamed out of port, you basically had your computers tightly coupled to the missions it was carried out. And there was next to no way to change that other than to have things degrade in the course of a conflict or through operational wear. So this obviously provides a bit of a Procrustean bed that you have to live within. And there's a number of reasons why this is very problematic. One reason, of course, is static allocation means that if you end up encountering more threats dynamically than you were provisioned for when you steamed out of port, you're really out of luck. So if you end up having more missiles than you expected, there's no way to take power from other parts of the ship or computations or resources and then apply it to the problem at hand. Another problem, of course, is these ships are intended to go into harm's way, so things will go wrong, things will get destroyed, and once again, once you've lost capability, you've lost pre-allocated capability. There's no way to adapt or reconfigure. The good news is that dynamic resource management is something that can be used here to help solve this problem. Well, I went to DARPA in the early 2000 timeframe, and one of the things I did while I was there was help to start a program called the Adaptive and Reflective Middleware Systems, or ARMS program. And back in those days, as you may recall, as Steve Welby, if he's still here, will recall, because he was my boss for a while, we had to go and sell our programs to the various services. So we worked very closely with the folks from the DDG 1000 program and PEO ships. So it was a joint effort. And what we did is we developed some very interesting adaptive resource management middleware and algorithms. And this, of course, is where it starts getting into the AI parts. As you can imagine, the configuration space for resource allocation is vast and combinatorially explosive. So there was no way we were going to be able to get perfect closed solutions. So instead, we ended up coming up with ensemble-based bin packing heuristics that would attempt to try to deal with the fact that any one algorithm or any one approach may not actually give you a good answer in a timely manner, but if you ran them all at the same time in parallel on the total ship computing environment, you'd be more likely to find what you need within the time that you had to allocate to it. So this was some pretty cool technology. A lot of interesting work went into that. And this allowed us to be able to have a system that would adapt to changing conditions as things came and went, be able to allow the commander to reconfigure what was important at any given point in time. So this was all very well and good. As a result of spending a lot of time and a lot of hard work building prototypes and doing analyses and running experiments, we created a bunch of results. So we were able to prove that using dynamic resource management would make the system more survivable under the scenarios that we were given by as challenge problems by the DDX or DDG 1000 program office. We were able to operate through failures and attacks in a more gracefully degrading way rather than the way things worked in the past. We were also able to come up with some really clever deployment optimizations and deployment models that could take so-called operational strings, which are basically groups of tasks at certain priorities that compete for the processing resources, and be able to reallocate and reconfigure them dynamically together as a group up and down based on the mission changes, which is a very hard distributed systems problem. And we were also able to demonstrate that the system could work even when things were broken. And this was great. We were feeling very proud. We were getting ready to go up for our go-no-go decision, which was the thing that Dr. Tether did in those days to see if programs got to go to the next step. And then something went wrong. We started to talk with the folks who did the certification portion of DDG 1000, and then they said, there's no way we're going to take all this cool technology you've done and actually transition it to the ship because we can't convince ourselves it's going to work correctly. And we would go and talk to the folks who were running the program office and show them all of our simulations and all of our prototypes and our tests and experiments, and they'd say, that's great, but we can't get the Weapons System Explosive Safety Certification Board, the WEAVCERB, to buy off on this because we can't prove this is going to end up not having unstable states, incorrect states, unusable states, unsafe states. So we were a bit flummoxed, and we started looking around, and we read a lot of the documents that were available at the time to explain what these folks did. And we noticed some interesting things. This is part a technical problem, but it's also sort of a socio-technical problem, because part of this has to do with culture and the way people convince themselves something is trustworthy or risk prudent to adopt it. The way that people build these combat systems in those days, and unfortunately largely still today in many ways, is to do everything with static resource allocation. And there's a variety of reasons for doing that. It's very efficient, low overhead, and so on. But it's also well supported by existing practice. People who run the certification boards, people who do the analyses, people who sign off on something being trustworthy, know the risk involved in trying to decide whether those things are going to work or not. We came along with our cool adaptive resource management approach based on these heuristics and the various search techniques and so on, and they were more survivable in some sense, but people didn't really know what to do about that. So that, of course, was rather disappointing. But since this was DARPA, when you run up against a roadblock, you don't give up, you pitch another program. So we went off and pitched a new program, which we called Certification of Adaptive Dynamic Computing Environments, or CADENCE. And the idea here was to try to see what we could learn, what lessons we could learn from our experience with ARMS in order to find out a way to make these kinds of more adaptive systems usable in the safety critical environments. So one of the things we did was we went back and re-examined our adaptive resource management approach we'd done with ARMS and tried to make it more certification friendly. And I think that's one of the lessons I kind of want to pass along as a general technique. Rather than trying to do something completely dynamic, which was very cool, but we couldn't convince anybody it would be certifiable, we took a step back and instead came up with groups of configurations that we could pre-allocate and pre-certify and then be able to switch around dynamically between those. So we were moving between various state configurations that had been more likely to be deemed as trustworthy than had we done a completely dynamic approach. And that was actually pretty interesting, and I'll talk a bit more about that in a second. The second thing we did is we worked on an integrated tool chain for doing assurance. And this involved a couple of different steps. So one thing we did is we had a bin, these ensemble bin packers I talked about, and we would use those to come up with thousands of potential configurations of allocations of resources that looked promising. And then we would go ahead and run those through a suite of formal analysis tools and simulators in order to try to reduce that to a more manageable 1,000 or so configurations. And then we would run those things through an automated test environment, which was reflective of the kinds of actual testing and operational test cases they would use in the ship, in order to come up with a much more tractable number, around 100 or so configurations. And that would then be the pool from which the resource manager would select at runtime in order to pick what would be deemed appropriate given the circumstances. And then also produced here, of course, was evidence for the review board to go back and try to convince themselves what we were doing made sense. So by the time we finished up this effort, we had gotten to the point where we could get pretty good confidence for this sort of hundreds of pre-generated, automatically generated configurations that we pre-certified. And that worked out pretty well. Unfortunately, as is often the case in these kinds of efforts, the funding ran out before the problems were solved. And so there's still, I believe, is a nice space here to be examined from the point of view of trying to go a little further, trying to look at more adaptive approaches, more dynamic approaches that do the monitoring on the fly. Now again, this was 2000, in the mid-2000s to the end of the 2000s. A lot of things have changed in the past decade that make this more tractable, especially in terms of the amount of computing we have. So even though we got things further along, there's still a lot of work left to do. So to go ahead and wrap up, adaptive, dynamic computing environments remain an important topic. It turns out that Dr. Suresh Jagannath from Purdue has started another program at DARPA called Building Resource Adaptive Software Systems, or BRAS, which is actually very much like what we were doing with ARMS. But the good news is that the world is ready for it now. We're doing a lot more work with things like mobile environments, cloud computing, things where adaptation really is more acceptable and more desirable. I still think, even after all this time has gone by, people really haven't solved this problem the way it needs to be solved for dynamic systems, although, as I mentioned, this sort of hybrid approach where you can pre-configure and pre-allocate things and get people satisfied that they're going to be robust enough, and then dynamically switch among them at runtime, that's a pretty good compromise. And I guess my other perspective from being at DARPA was that it's easier to pitch programs on adaptive solutions than certification of adaptive solutions, which is one extra level of complexity. So thank you very much.